The theory of constraints is a methodology for identifying the biggest limiting factor that stands in the way of achieving a goal. We often refer to this as the bottleneck of a system. The core idea is that every process has a limiting factor or constraint, and that process throughput can only be improved by addressing the constraint. Another important corollary to this is that in any expenditure of time, money, or effort, working to improve a step in a process that is not the constraint is a waste. Focusing your efforts to better utilize the constraint is the fastest way to improve profitability. These concepts were first introduced by Elihu Goldratt in his 1984 novel The Goal, where he used storytelling to walk the reader through the life of a production manager as he learns to think logically about the problems he's presented with and gradually uncover the cause and effect relationship between actions and results. It's important to note that this book was written before the machine that changed the world. So many aspects of the theory and use of the scientific method to understand and improve operations was happening at the same time the world was working to understand the Toyota production system. There's a lot of overlap between theory of constraints and lean, particularly in how we identify waste, map, measure, and work to continuously improve the system. Let's break down the theory of constraints a bit more so we can see how this aligns with our conversation of flow. For this content, I'm going to be pulling from the Theory of Constraints Institute, which works to provide knowledge, workshops, and coaching around the theory for organizations and practitioners. The theory of constraints, also often referred to as just TOC, is often described by using the chain analogy. No chain is stronger than its weakest link. If you try to strengthen any other link, it'll be wasted time and effort, as your weakness is the same. Think about this from a flow standpoint. If our pacemaker process can't work to tact, what sense does it make to focus on improving capacity at any other process? Not only does it not make sense, it makes the situation worse. We now have increasingly unlevel flow, which results in inventory, waiting, and downtime at other process steps. In the chain analogy, increasing strength anywhere besides the weakest link will make the chain more fragile, given the extra weight and weakness at the constraint. Let's take a look at how this work applies to a non-manufacturing example. Since it's what I know best, I'm going to use another healthcare example. Let's think about patient flow within the hospital. In this case, a patient is coming in for an orthopedic surgery, which typically requires a 2-day stay in the hospital. Like value stream mapping, using theory of constraints forces us to take a systems view. The operating room in this hospital is like many others across the U.S. It's the revenue generator for the health system, and it suffers from issues like first case on-time starts and long turnover times, which negatively impact OR efficiency. So much so that the OR is running at about 65% efficiency, as measured by the time a surgical procedure was in process, or the time from cut to close, as compared to total available OR minutes, including 30 minutes allocated to room turn. The senior leadership team makes this a strategic priority for the health system and focuses on opportunities to increase efficiency in the OR. Makes total sense, right? Well, sort of. We can use theory of constraints to help us understand our biggest constraints within room turnover and first case on-time starts, but we need to recognize our role relative to the larger system. If inpatient bed utilization is consistently running at 95%, where are these patients going to go? What we see happen, and what we do see happen, is that patients get boarded in post-anesthesia recovery waiting for a bed. So much so that occasionally patients wait in the OR to be moved to the post-anesthesia recovery unit. This now becomes a flow issue. So it's important to understand flow and the theory of constraints at both the local and the macro level. If making local level improvements, be sure that the larger system is in a position to accommodate your increased throughput. Otherwise, you're creating additional issues within the system. It's all about the flow. Think about your operations. Work to leverage your value stream to understand capacity at each step in the process. A system can produce only to the bottleneck's capacity. So in this case, this system would be capable of producing a maximum of 40 units per day. If you're focused on utilization of your value-added processes, as many modern managers are, you're going to wind up with a lot of inventory in this process, which hides defects, adds cost, and creates such an enormous buffer that we can't truly understand the needs of the system. As we work to understand this, we want to understand the capacity of each process step, in addition to the bottleneck time and the throughput time. The bottleneck time is the time of the slowest workstation, where the throughput time is the time it takes a unit to go through production from start to end. In this case, our bottleneck time is 4 minutes, while the throughput time is 9 minutes. Again, this is a very simple example, but use it to think critically about your process, capacity, bottleneck times, and throughput time. Let's take a look at something most of us have probably experienced: ordering a sub at Subway. The typical process consists of ordering, first and foremost, your bread, which the sandwich artist, Subway's term for their employees, gets from the refrigerator. Then they fill it based on your order, adding condiments and items based on your feedback. Next, the sub goes into the toaster before it's wrapped with a napkin and put in a bag as you pay. If you've been to Subway recently, this process is pretty accurate. While there are usually 2 sandwich artists, we can feel the bottleneck at the single cash register. Let's take a look at how this process breaks down from a constraint and throughput perspective, which impacts our overall system capacity. There are 2 sandwich artists that are each capable of delivering a sandwich every 20 seconds. At 37.5 seconds, wrapping, payment, and delivery has the longest processing time and is the system bottleneck. We calculate the capacity of the system by dividing the total available time per hour, which is 3,600 seconds, divided by 37.5 seconds, which tells us that the system is capable of delivering 96 sandwiches per hour. Finally, the throughput time of the system is 122.5 seconds. The theory of constraints suggests taking a 5-step approach to identifying and addressing system limitations, which include identifying the constraints, developing a plan for the constraints, focusing resources on accomplishing step 2, reducing the effects of constraints by offloading work or expanding capability, and once that's all done, go back to step 1 and find the new constraint. We walked through a simple Subway example where we identified the system constraints. In more complex systems, we may want to employ a process capacity sheet. The process capacity sheet, as the name implies, helps to determine process capacity, and thus our ability to meet takt time. This is determined by calculating each step's capacity, considering the available time per shift, completion time, changeover time, and any other relevant factors for each step in the process. You can find templates and examples of these for use in both manufacturing environments and in non-manufacturing environments. The biggest difference on these forms are the focus on equipment or machine runtimes. While these aren't as prevalent in office or service settings, there are occasionally technology-driven processes that we need to capture, and we need to be sure to capture the setup time required for any of this equipment. All of this information can help us to clearly identify our bottleneck. We may already have a pretty good handle on where it is, but this added level of detail is necessary to help you think through strategies that will get you to where you need to be. In the book The Goal, Goldratt uses an example of a Boy Scout troop hiking up a mountain. The hike, like many processes, is a set of dependent events, all with statistical fluctuations. For example, each boy in the hike fluctuates in speed. One out-of-shape little boy ends up slowing down the group. Some kids are way ahead, while others, walking with and behind this boy, are going slower than what they're capable of. This creates a lot of variability in a system that's totally out of sync. Enter Goldratt's theory of drum buffer rope. The drum buffer rope system is a key concept in the theory of constraints. Its purpose is to balance the flow of production, or in the case of a scout troop, to keep all of the scouts hiking at the same pace. The slowest scout, Herbie, aka the constraint, sets the pace. This is the drum. This sounds, no pun intended, an awful lot like takt and the pacemaker, but there is a key difference here. While a lot of people think the bottleneck from theory of constraints and the pacemaker and lean thinking are the same thing, they are not. While both TOC and lean work mostly in conjunction, we want to be careful about the differences. In both TOC and lean, we want to seek out and break the bottleneck. But in lean, we do not want the bottleneck setting the pace of production exclusively. This is primarily because the bottleneck may exist for a lot of reasons: downtime, long changeovers, things of those sort. In the words of John Shook, why would I choose to let an operation with such problems determine the way I flow my entire value stream? Of course, I have to deal with the bottleneck, but I will not let it dictate the pace or takt of my entire product flow. Okay, let's get back to the Boy Scout troop and the out-of-shape scout, Herbie. Herbie is what we refer to as the drum. The rope extends to the first person in the line, which cannot walk faster than the drum. This is what we mean by having the bottleneck be the drum. We do not want any of our upstream processes producing faster than the drum. That results in a lot of inventory and disjointed, uneven processes. The buffer is a small amount of inventory that's utilized to make sure the bottleneck is always operating at full capacity. In the analogy of the hike, this allows our bottleneck Herbie to keep walking, even if somebody in front of him stops to tie their shoes. We want to make sure Herbie keeps walking. Now, this is where TOC and Lean, again, differ just slightly. Instead of intentionally creating a small lot of inventory, we can leverage a Kanban pull system to synchronize material and information flow and disconnected processes to enable just-in-time production, which we'll get into in more detail in the upcoming lecture. But let's round back to our famous Herbie. Herbie doesn't always need to be the bottleneck. In fact, in this story, his team takes his backpack to help increase his speed. Let's take it a step further and assume that with time, exercise, and the growth mindset, Herbie gets fit and quickly loses his bottleneck status. Great for Herbie, and our system has improved. But we know we now have a new bottleneck to address. Both theory of constraints and Lean teach that bottlenecks must be identified and broken. In Lean, we know that if a process cycle time is greater than takt time, we have an issue that must be resolved. Also, the drum buffer rope concept is very similar to pull. There are some slight differences, but in large part, the intent and approach is very similar. It's always important to stop and reflect on the application of these concepts to non-manufacturing industries and applications. Instead of talking about high-level applications like Subway, let's look to companies that have actually used these concepts to improve their business. Microsoft published a case study about their use of TOC to address issues in change requests within one of their engineering teams. This specific team was responsible for small change requests involving less than 120 hours of development work. Their backlog had grown so much in a short period of time that their lead time for a change request was over 5 months. Due dates weren't met, and internal customers were unhappy. Sound familiar? In this case study, they found that the biggest bottlenecks and system constraints were not in the engineering work itself, but in the management, planning, scheduling, and queuing of the work. With no new resources and no changes to how the team performed software engineering tasks like design, coding, and testing, the changes to how the work was queued and estimated resulted in a 155% productivity gain in 9 months. The lead time was reduced to a maximum of 5 weeks. Due date performance improved to better than 90%. The backlog was worked off, and the department is no longer seen as an organizational constraint. Where could this type of analysis and application of drum buffer rope be applied to your organization?